I want you to start by picturing a seemingly impossible geometric challenge.
Oh, okay.
Yeah, imagine trying to take the entire Earth, right? Like this massive, bumpy, completely three-dimensional sphere,
Right.
and it's covered in jagged mountain peaks, deep ocean trenches, sprawling valleys, and you're trying to flatten it out onto a perfectly smooth two-dimensional digital screen.
It is a massive geometric and mathematical puzzle.
Yeah.
I mean, you are fundamentally taking something with infinite volume and texture
Yeah.
and trying to force it into a constrained, flat plane, without losing the integrity of the data.
Which is wild. How do you do that without completely warping the true shape of the world?
Well, it's tough.
Right. Like, how do you look at a flat screen on your phone and know the exact grade of a steep cliff?
Ah.
Or calculate precisely where millions of gallons of rainwater will pool after a storm?
Yeah, exactly.
So welcome to this deep dive. Today, we are exploring the study materials for the GISP exam.
The Geographic Information Systems Professional Certification.
That's the one. Specifically, we are zeroing in on Section 303. That one's titled Understanding of Surface Interpretation and Representation.
Which I know sounds incredibly academic.
It really does.
But it is the absolute bedrock of modern geography and spatial analysis.
Yeah.
Whether you are actively prepping to sit for this GISP exam and need to nail down the mechanics of these spatial models, or you're just a professional who wants to understand the invisible math powering the digital maps we rely on every single day.
To navigate our world, basically.
Well, exactly. Mastering this material is critical.
We are going to decode the terminology, the core concepts of surface modeling, and really the underlying mechanics of map reading. So, okay, let's unpack this.
Let's do it.
Before we even look at a specific map, the text establishes two foundational pillars of GIS that we have to separate, right? Surface interpretation and surface representation.
Right. And separating those two concepts mathematically and conceptually is really where the exam prep starts.
Okay.
Let's look at surface interpretation first. This is highly analytical.
Okay, so more about analyzing than building.
Exactly. This is the process of taking spatial data and uncovering the patterns, the relationships, and the trends across a landscape.
Give me an example of that.
Sure. So if you are looking at an elevation model, interpretation is the act of running an algorithm to identify where the watershed boundaries actually divide.
Oh, I see.
Or if you are looking at climate data, it's the analytical process of mapping out temperature gradients over complex terrain.
Right.
It is the human or algorithmic process of understanding what the geometry of the landscape dictates.
So it's extracting functional meaning from the raw data.
Yes.
Understanding the scale, the direction, and how those landforms interact in both 2D and 3D space to cause real-world effects.
That's spot on. Surface representation, on the other hand, is the technical architecture.
The structural side.
Right. It focuses on the actual data structures and methods we use to digitally model those surfaces inside a computer system.
Okay.
This is where you get into the hard mechanics of tools like raster grids or TINs.
Which stands for triangulated irregular networks, right?
Got it. Right.
Let's break down the mechanics of those representations because they handle data completely differently.
Totally differently.
Representation is essentially choosing your medium. Whether you're painting with watercolors or oil paints, right?
That's a great way to put it.
You are deciding how the computer is going to store this reality. Like a raster grid stores data using a uniform matrix of pixels where every single square holds a specific z-value, like elevation.
Yeah, and what's fascinating here is that these specific representation techniques, rasters and TINs, are uniquely designed to solve a major computing problem.
Which is?
Handling continuous phenomena.
Oh, okay.
See, computers inherently prefer discrete binary data, things that fit into neat boxes.
Right, 1 or 0, black or white.
Exactly. A property line is discrete. It stops at a fence. But elevation doesn't just stop.
Right, it's a slope.
It is a continuous surface across the entire globe. Temperature is continuous. Rainfall is continuous.
Meaning there are infinite values between any 2 points. You can't just draw a box around a mountain.
No, you can't. You need a data structure that can represent something that flows and changes gradually without ever breaking.
And that's where rasters come in.
Yeah, a raster handles this by blanketing an area in that uniform grid of pixels you mentioned. The smaller the pixels, the higher the resolution.
but the heavier the file size becomes, I imagine.
Exactly. If you want to model a mountain range at a 1-meter resolution using a raster, you are asking a computer to store millions of individual pixel values,
Wow.
even for a flat plateau where the elevation isn't changing at all.
Which seems super inefficient, and I'm guessing that is where TIN's triangulated irregular networks come in to solve that storage inefficiency.
You nailed it.
Oh,
Instead of a uniform grid of heavy pixels, a TIN uses vector data.
okay.
It takes a set of known sample points and connects them to create a 3D mesh of non-overlapping triangles.
So the beauty of a TIN is its algorithmic efficiency, right?
Yes, because the network is irregular, the algorithm can adapt to the complexity of the terrain.
Ah, I get it.
So if you are modeling that flat plateau, a TIN might use one massive triangle to represent 1,000 square meters.
Because the elevation doesn't change, so you don't need a million little pixels.
Precisely. But the moment you hit a jagged cliff face, the algorithm clusters thousands of tiny, dense triangles together.
To accurately capture the sudden, chaotic changes in the surface.
Exactly.
So you optimize your processor power, you spend your computing budget on the complex terrain, and save it on the flat areas.
Which a raster simply cannot do.
Right. Okay, so since representation gives us these different data structures to capture the continuous world, let's shift to how we actually collect that data visually.
Sure.
The source text highlights aerial map interpretation, which is capturing the Earth from above with aerial photography or satellite imagery.
And the text outlines a highly systematic approach for reading these images.
Right, it's not just taking a quick look.
No, aerial map interpretation is not just casually glancing at an orthophoto. It requires a formal geometric breakdown.
Okay, what's the first step?
The first step is actively looking for recognizable spatial patterns.
Like shapes.
Yeah, the human eye and spatial algorithms both have to be trained to differentiate the strict anthropogenic geometry of human development.
You mean like the perfect straight lines of highways?
Exactly. Highways, the right angles of industrial buildings, differentiating that from the organic fractal shapes of natural rivers and forests.
Okay, but geometric shapes alone don't give you spatial context, do they? You need mathematical scale.
Right.
We know a scale bar translates map distance to ground distance, but for a GIS professional looking at an aerial photo, scale is about calculating the physical footprint of those geometric shapes, right?
Yes, to confirm what they actually are. The scale dictates the classification.
How so?
Well, from the sky, a massive multi-lane interstate and a small rural aqueduct might both register as linear gray features.
Oh, that makes sense.
But by applying the scale mathematically to the pixels, you calculate the width. If the feature is 80 feet wide, it's an interstate.
And if it's 10 feet wide, it's an aqueduct.
Exactly. Then the third step the text mandates is direct comparison.
Cross-referencing.
Yeah, you cross-reference that unclassified aerial photograph with the symbolized, verified data set to ground truth those spatial anomalies.
Okay, I have to push back on this a little bit, or at least look at the underlying mechanics here.
Sure, go for it.
Because an aerial photograph is a 2D image. It just has an X and a Y axis.
Right.
But if the entire goal of this GISSP exam section is understanding surface and elevation, the Z-axis, how do you mathematically extract depth from a completely flat array of pixels?
That is the ultimate limitation of a single photograph.
Right.
And overcoming it requires the interpreter to rely on geometric cues baked into the 2D image.
Cues like?
Specifically shadows and perspective. You are using the physics of light to guess the Z value.
Oh, wow. Because if you know the exact time of day the photo was taken and you know the geographic coordinates, you know the precise angle and azimuth of the sun.
Exactly. You are doing trigonometry on the fly.
That is wild.
By analyzing the length and direction of a shadow cast by a cliff face or a building, a GIS algorithm or a trained professional can calculate a highly accurate estimate of its height.
So like a 300-foot radio tower will cast a very specific shadow length at 2 p.m. in October.
Yes, exactly. And there's also the perspective shift of taller objects. It's called relief displacement.
What's that?
It's where a skyscraper appears to lean outward away from the exact center of the camera lens. That also provides measurable mathematical clues about vertical height.
Okay, so shadows and relief displacement give us a great visual calculation, but it is still an estimation based on a 2D image.
Right, it's an estimate.
You can't engineer a structural bridge or map a floodplain based on the trigonometry of a shadow.
Definitely not.
To get hard, undeniable math, we have to translate that visual data into a topographic map.
And this is where we transition from interpretation into pure quantitative data.
Okay.
Topographic maps represent the Earth's surface using contour lines. And the exam text draws a very sharp necessary contrast here between a topographic map and a planimetric map.
Okay, so if a topographic map is our 3D mathematical blueprint, a planimetric map is what I'm looking at on a basic subway map or a standard street atlas, right?
Yeah, exactly.
It is strictly 2D flat geometry. It shows horizontal distances and directions, but completely ignores the z-axis.
Right. A planimetric map will give you the most efficient routing from point A to point B. But it won't tell you if point B is sitting at the summit of a 1,000-foot mountain, which obviously changes the nature of your route.
Yeah, a subway map isn't going to help you climb a mountain.
Exactly. A topographic map embeds those contour lines to inject the third dimension into a 2D plane.
Here's where it gets really interesting for me. The defining rule of a contour line is that it connects points of equal elevation, right? So if you were to physically walk along a single contour line on a mountain, your elevation would never change.
Right.
Your X and Y coordinates are constantly shifting as you move north, south, east, or west, but your Z value is locked. It's like wrapping entirely around a mountain without ever taking a single step uphill or downhill.
That concept is vital for the exam. You are literally creating a horizontal plane of data.
Right.
And the vertical distance between those horizontal planes, so the elevation change between one contour line and the immediate next one, is the contour interval.
Okay, so if your contour interval is set to 10 feet, every time you cross a line on the map, you are mathematically documenting a 10-foot change in the z-axis.
Exactly. This is how a GIS professional reads slope from a flat screen. The spacing of the lines dictates the gradient.
Makes sense.
If the contour lines are widely spaced apart on the screen, the algorithm reads a very gentle, flat slope.
Because the horizontal distance, the run, is massive compared to the vertical distance, the rise.
Right, you have to travel a long way horizontally just to gain 10 feet of elevation.
But if those contour lines are densely packed together, like stacking up on top of each other.
You have a steep cliff.
Yeah.
The rise is happening with almost zero horizontal run. The geometry of these lines allows software to instantly visualize terrain features.
I see.
Concentric circles of contour lines mathematically represent peaks or depressions.
Oh, like a volcano crater or a hilltop?
Exactly.
Yeah.
V-shaped contour lines pointing upstream represent river valleys, while V-shapes pointing downhill represent ridge lines.
So you are literally reading the structural math of the mountain.
You are. And while you extract this data, the text stresses the absolute necessity of understanding map orientation, specifically magnetic declination.
Okay, let's talk about that. Which, on a basic level, is the difference between true north, so the geographic North Pole, and magnetic north, which is where a compass actually points.
Right.
But for a GIS professional building a spatial database, it's not just about knowing how to hold a compass in the woods, right?
No, not a lot.
It's about how algorithms reconcile shifting magnetic fields across historical data sets.
Yeah, it is a massive data management issue. The Earth's magnetic field is constantly shifting. Magnetic north today is not in the same location it was in 1990.
Wow. Okay.
So if you are overlaying a historical topographic survey from 30 years ago onto a modern GPS data set, the declination values are different.
I didn't even think of that.
If the software doesn't algorithmically account for that historical shift in magnetic declination, the math layers will not align.
Over a small area, maybe it doesn't matter too much, but if you are laying a 50-mile oil pipeline,
Right.
a 2-degree error in declination means your dataset is completely detached from physical reality by the time you reach the end of the line.
You will miss your target entirely. The math has to be absolute.
Okay, so we have this quantitative data now. We can calculate the slope, the exact distance, the contour intervals, the relief of the land.
Yep.
How do GIS professionals actually process this data to build out real-world solutions?
The immediate application is constructing topographic profiles and cross-sections.
Okay, how does that work?
You draw a transect line across your digital elevation model, say, across a river valley.
Like a straight line slicing across the screen.
Exactly. The GIS software samples the z-values of every pixel or triangle that intersects that line and plots them on a graph.
Oh, cool.
You instantly generate a cross-section view as if you sliced the valley in half and are looking at it from the side.
Which is the exact math a civil engineer needs to know if, like, a planned mountain highway has a slope percentage that is too steep for commercial trucks to safely ascend.
Right. It dictates the physical engineering of our infrastructure.
Yeah.
And this process of sampling data points across a model leads us directly to arguably the most complex and crucial sample question from the GISP exam provided in our text.
Oh, the big one.
Yeah, the question focuses on the mechanics of surface interpolation.
This is a major concept that takes up the entire back half of our focus today. The exam question asks which statement about surface interpolation in GIS is fundamentally true.
And if we connect this to the bigger picture, the answer to this question explains how almost all modern digital mapping actually functions under the hood.
Okay, let's hear it.
The correct answer states that surface models allow you to store information by taking scattered samples of values at different points and then interpolating, estimating, or calculating mathematically between those known points.
Okay, think of it like the most advanced game of connect the dots ever created.
That's a great analogy.
Because you don't actually go out and measure the elevation of every single square inch of a mountain. Even with drones and LiDAR, collecting, processing, and storing infinite data points is computationally impossible.
Exactly. It's impossible. You are always dealing with gaps in the data. You have a grid of known sample points.
Right.
You know the elevation exactly at point A, and you know it exactly at point B, which is 50 feet away.
But you have nothing in between.
Right. The computer has no actual data for the 49 feet between them.
Yeah.
So the GIS software has to interpolate.
It fills in the blanks.
Yeah, it runs spatial algorithms to look at the known values, analyze the distance between them, and make a mathematically rigorous calculation of what the continuous terrain looks like in that empty space.
So it's essentially using calculus to guess the curves of the landscape.
Yes, exactly.
And those algorithms rely on a fundamental concept, spatial autocorrelation,
Right.
which is the idea that things closer together are more related than things farther apart. So if point A is 100 feet in elevation and point B right next to it is 90 feet, the algorithm assumes a gradual downward slope.
But that highlights the danger in the skill of interpolation, which is what the exam tests.
How so?
Well, what if there is a massive 50-foot vertical drop, like a sheer cliff, right between point A and point B?
Oh, wow.
If you use a basic interpolation algorithm, the software will just smooth it out into a gentle slope, completely erasing the cliff from the digital model.
Because it just assumes a smooth transition, which is why GIS professionals have to introduce break lines into their TINs and rasters to tell the algorithm, stop smoothing here. This is a hard edge.
Yes, you have to know which mathematical interpolation method to use based on the reality of the terrain.
Okay.
Are you using inverse distance weighting, where known points lose influence the further away they are, or are you using kriging, which applies advanced statistical probability to the estimates?
It sounds super complex.
It is. The software will always give you a beautifully smooth 3D model, but if you chose the wrong interpolation method, that model is a mathematical fiction.
So what does this all mean? Like, why does the accuracy of this interpolated digital model matter outside of an exam room?
Well, the real-world applications dictate massive physical and financial decisions.
For example.
In engineering, this interpolated data is used for cut-and-fill analysis. Before a construction company bids on building a new stadium, they run these surface models.
To figure out the dirt, basically.
Yeah, to calculate exactly how many thousands of cubic yards of earth they need to cut out of a hill and how much they need to fill in to create a flat foundation. If the interpolation is off by a few percentages, the bid is off by millions of dollars.
Oh, wow. That's huge. And in geology, it's used for mapping geomorphology and predicting hazards. You run surface models to analyze slope stability.
Absolutely.
Because you can't predict where a landslide is going to wipe out a highway without an incredibly accurate, interpolated model showing the exact relief and drainage patterns of the mountainside.
Exactly. And in forestry and ecology, we use these models for viewed analysis and solar radiation tracking.
How does that work?
By mapping the continuous surface, you can model exactly how sunlight hits different aspects of a valley at different times of the year.
Oh, that's brilliant.
Right. That tells you precisely where certain temperature-sensitive species will thrive, or where the vegetation is dry enough to act as a catastrophic fuel source for a wildfire.
And all of that relies on the software correctly estimating those empty spaces between the data points.
Yes, all of it.
That brings us back to you, our listener. If you are sitting for the GISP exam soon, mastering these specific mechanics is going to be the key to passing Section 303.
It really is.
You need to be able to clearly articulate the structural differences between vector TINs and pixel-based rasters. You need to know how contour intervals mathematically dictate slope, and you must internalize the algorithms behind surface interpolation.
And you also need to demonstrate the distinction between visually interpreting geometric patterns on a 2D aerial photograph using scale and shadow
Right.
versus extracting hard quantitative 3D data from a topographic database.
Yeah.
They require completely different analytical skill sets, and the exam expects you to know exactly when to deploy which method.
Definitely. And if you are just listening out of professional curiosity, hopefully you can now look at the 3D terrain on your phone's map app with a much deeper appreciation.
Yeah, I hope so.
You're not just looking at a picture, you know. You are looking at a highly processed, continuous matrix of spatial data built on millions of interpolated mathematical guesses, designed to render a bumpy world onto a flat screen.
It really is a phenomenal achievement in spatial geometry that runs quietly in the background of our daily lives.
It leaves me with one final thought based on what we just unpacked about interpolation.
Okay, let's hear it.
We established that our most advanced surface models rely heavily on taking scattered sample points and having an algorithm calculate the unknown spaces between them.
Right.
But the physical world is volatile. Coastlines rapidly erode, rivers carve new channels, urban development moves millions of tons of earth overnight.
Yeah, the Earth is always moving.
As our physical environment changes faster and faster, often much faster than we can afford to physically go out and run new LiDAR surveys or collect new sample points, it makes you wonder.
Yeah.
How much of the continuous digital terrain we rely on for major infrastructure and ecological decisions is actually just a highly educated, mathematically interpolated guess about spaces that have already fundamentally changed?
Wow. Yeah, that raises an important question about the shelf life of spatial data in a rapidly changing world.
It's something to think about the next time you look at a digital map and assume it represents absolute, real-time reality. Thanks for joining us on this deep dive.